Hello everyone, this is part 2 of section 1.5 where in part 1 we learned how to solve first order linear differential equations that were not separable by using the integrating factor, and so there's our last example that we had gone over. So now we look at applications involving what we call mixture problems. So with mixture problems we have a solute and a solvent. Typical example is salt and water, or brine. So here's the idea. Let's consider, I'm going to draw a little diagram here, and we'll consider a tank. So I'll make a little cylinder looking tank. I'll clean that up a little bit. Okay, so there's my tank, and maybe it's empty, or maybe it has some brine in it, or solute and solvent, so that'll be my level of the volume that's in the tank. And we'll have an input, so this will be my little spigot. Let's say that that's our input. And then we'll have an output. It'll be at the bottom of the tank. And that's our output. Okay, so let's say that something, a volume of, it could either be pure water or maybe a mixture of water and some of the solute, or whatever it is. With regards to the input, we'll have a rate of input, so we'll indicate that by R sub I. So that's going to be our rate. And let's give it some units. We'll go with the British system. We'll say gallons per minute, just to get a good feel for the concept. We'll include units. And there's some concentration. We'll call it C sub I. So either it's pure water and concentration would be 0, or maybe there's an amount of solute with the solvent, or salt with the water. Let's go with salt with the water, it makes it easier to talk about it. And let's say there's so many pounds per gallon. Okay, so that's going to be our input. Now the output is going to be at a particular rate, and it will have a concentration also. Now notice that the rate in and the concentration in will be constant. So let's mention that. So the constants are the rate in, the concentration in, and also the rate that it's coming out. But the variable could be variable, could be constant as well. So let me say variable possible is the concentration coming out. Now, if we talk about what's in the tank at any time, we have an amount that we'll call x of t. So this will represent the amount of solute. So in terms of units, we'll say pounds. So that'd be the amount of salt, let's say. There's a certain volume in the tank, which could be constant or it could be changing. So it's a function of time as well, because the amount typically would be changing. And if we're talking about our units, that would be gallons. And then we have our concentration at any time. So the concentration at any time, again, is going to be given, we'll call it C sub O, which will be a function of T, and that'll be just the ratio of the amount X of T over the volume V of T. So the variable we'll say is the concentration coming out, which we'll just call X over V. Alright, so that's our scenario. Now, with regards to, and the units for this concentration would be pounds per gallon, because the amount is in pounds and the volume is in gallons. Okay, so that's a very important idea, that the concentration coming out could vary. Alright, so we'll call X sub I the amount coming in. And that's going to be the rate times the concentration times the change in time. So you've got your rate, which is in gallons per minute, times the concentration, which is in pounds per gallon, so the gallons cancel, and times your change in time, which let's say is in minutes, and so we just get pounds. So that's the amount coming in. The amount coming out, similarly, will be the rate out times the concentration out times the change in time. So therefore, the change in the amount, so delta X, we'll say, is the amount in minus the amount out. So if you've got more coming in than is going out, then there's going to be an increase, or vice versa. And that'll just be the rate in times the concentration in times the change in time minus the rate out times the concentration out times the change in time. So then if from this expression we factor out delta T, we're left with R sub I, C sub I, minus R sub O, C sub O. That's O, not 0. And then if we divide by delta T, we get delta X over delta T is R sub I, C sub I, minus R sub O, C sub O. And then if we take the limit as delta T tends towards 0, of the change in the amount over the change in time, and there's no need to introduce a limit here because there's no time variable. We then realize that this limit represents the derivative or the time rate of change of the amount, dx dt. Okay, so that's our main formula. That's the development of our formula. So when we have these mixture problems, that's the formula, primary formula that we're going to use. So we have to identify rate in, concentration in, rate out, concentration out, and realize the concentration out could be a variable, X over V. Okay, so here we're considering a reservoir with volume of 8 billion cubic feet. And there's an initial pollutant concentration. So let me just make a little sketch. It's a reservoir, so let's see, there's my reservoir. These little lines will represent the land. Okay, so there's my reservoir, and it's got a volume of 8. Okay, let's go to scientific notation. Billion is 10 to the 9th. And that's feet cubed. Okay, so then it goes on to say that there's an initial pollution concentration of 0.25%. So at T equaling 0, the concentration is 0.25%, which will convert to a decimal, 0.0025. So one thing to note is that the amount at this time, because we're going to be able to find, since our equation involves the time rate of change of the amount, we might want to consider what is the amount at that time. So we would use the formula that x equals c times v, because of the fact that the concentration is x over the volume. So if we solve for x, we get x equals c times v. So the amount of this solute in this pollutant in the reservoir initially is going to be the 0.0025. Let me do it here. 0.0025. Okay, that really represents parts per cubic foot times the volume of 8 times 10 to the 9th cubic feet. And so we get that the amount is 20 million parts, okay, of this pollutant. Okay, so remember our formula is the time rate of change of the amount is R sub I, C sub I minus R sub O, C sub O. So let's determine R sub I. Okay, if we read further, there's 500 million cubic feet of water coming in, a daily inflow. So that's 500 times 10 to the 6th cubic feet. Or let's say 5 times 10 to the 8th cubic feet. The rate of the concentration, well, let's say the rate out. Here's the concentration in. Maybe we'll go for that next time. Okay, so then the concentration in is 0.05%, which as a decimal be 0.005, and that's parts per cubic foot. Okay, and then our rate out is, it says an equal daily outflow. So we'll just jump right to 5 times 10 to the 8th cubic feet. And our concentration out, again, is the variable. That's going to be the amount x at any time, which also changes, over the volume at any time, which could be constant. And in this case, the volume at any time is constant because the rate in and the rate out are equal. So we'd have the x, the amount of pollutant, over 5 times 10 to the 8th. And we want to include the units there. Alright, so now we substitute into our formula. Okay, so I'll reiterate it here. dx dt is r sub I c sub I minus r sub o c sub o. So that'd be r sub I 5 times 10 to the 8th times concentration in 0.005 minus r sub o 5 times 10 to the 8th times the concentration coming out, which again is variable, x over oh, I'm sorry, the volume, this volume here, that's a mistake, and because that's the volume inside the reservoir. That 5 times 10 to the 8th is the rate coming in and rate coming out, but the volume in the reservoir is 8 times 10 to the 9th. And actually I made some unit errors as well. This should be feet cubed per day, and the rate out is feet cubed per day. Okay, so now we're all set. So 8 times 10 to the 9th. Alright, so then we'll say that dx dt is equal to, if you multiply these two guys together, you get 250,000. And then minus, if you divide these two, you get 0.0625x. And we'll set this up so it fits the form for our standard form for our linear differential equation. We'll move the x term to the left-hand side. So that becomes plus 0.0625x equaling 250,000. So the analogy at this point, in terms of the standard form, remember it was dy dx plus p of xy equaling q of x was their standard form. But now we're saying dx dt plus p of tx equals q of t. So that's the analogy for the variables that we're dealing with. So this is a linear first order that fits this form, and so we need the integrating factor. Now we usually just say rho. I want to be more precise here and say rho of t, because t is the independent variable. So e to the integral of p of t with respect to t. So that would be e to the integral of 0.0625, but that's with respect to t. So that gives us e to the 0.0625t. So then we multiply. And so we have e to the 0.0625t times dx dt plus, I'm going to write the 0.0625, then the E, slide the E in there, then times X, equaling the 250,000, and I make sure again we multiply this side by the integrating factor as well. Okay, so now the left-hand side is expressible as the product of the derivative of e to the 0.0625t and x, and that's equal to the 250,000 times e to the 0.0625t. So now we're going to integrate both sides. I'm just going to throw the integral symbol in front of each side here and add the differential dt to the right. Okay, and then when we integrate the left-hand side, integrating the derivative of something, we just get the something. So e to the 0.0625t equaling, okay, remember the formula here for e to the kx, when integrating e to the kx with respect to x, recall we get 1 over k e to the kx plus our constant. So this becomes 250,000 over the 0.0625 times e to the 0.0625t, and we add our constant of integration. Okay, we're going to divide by the e to the 0.0625t, so it cancels here. We get 250,000 over the 0.0625, which is 4 million. And then plus, let's call it c e to the negative 0.0625t, because we're dividing by e to the 0.0625 and swing it up to the numerator and we get negative. Alright, so now the initial conditions, we'll be able to solve for c. We saw that when t is 0, x was 20 million. So we calculated that initially. So then that gives us that 20 million equals 4 million plus c, because t is 0, so e to the 0. So c is 16 million. Okay, so then that gives us our general equation. Let's call it x of t. So the amount at any time is equal to the 4 million plus the 16 million e to the negative 0.0625t. And now it had asked for how long for the concentration to reach 0.10%. So basically we want t equals question mark when x equals 0.10%, which is 0.001, and we'll have to find that as an amount. So that's the given, I'm sorry, that's not X, that's the concentration, right? So we'll have to find the X. So just like we did with the initial conditions, X is V times C. So that's the 8 times, we listed it as CV, sorry. X equals C times V. So that's the concentration, 0.001 times the 8 times 10 to the 9th, which gives us 8 million. Okay, so therefore 8 million will equal 4 million plus 16 million e to the negative 0.0625 t. And now we want to solve for t. Okay, so we've done this more than a few times. Let's think of the process. First, we're going to subtract 4 million from both sides. So we'll get 4 million. We're going to divide by the 16 million to isolate the E. And so let's cancel out the millions. Basically get 4 over 16. But then to undo the E, we're going to take the natural log of that. And then ultimately divide by the negative 0.0625. Okay, so you can check out the calculations, and I got 22.18, and that would be days. Okay, so a little bit involved, but kind of fun and interesting. And so one last example of another mixture problem. Here we have a tank initially containing 60 gallons of pure water, and brine's coming in. So let's draw a little diagram. So there's my tank, and initially the volume is 60 gallons, and the concentration is 0 because it's pure water. So then it says brine coming in, so let's do the rate in. It contains 1 pound of salt per gallon, and it enters the tank at 2 gallons per minute. So the rate in is 2 gallons per minute, and the concentration in is 1 pound per gallon. Alright, so then our rate out is, as we read on, perfectly mixed solution leaves at 3 gallons per minute. And it goes on to say the tank is empty after exactly 1 hour. And that's because it's losing every 1 minute it's losing 1 gallon because the rate in is less than the rate out by 1 gallon. So every first minute there's 1 gallon less and so on. So after 60 minutes, the 60 gallons are gone. And we want to find the amount of salt in the tank after t minutes. So x of t basically will get us to that point, right? And that's what we want to find. X of t. Okay, so then the concentration out. Remember, that varies because the amount varies. The volume could vary. In the last example, the volume did not vary because the rate in and the rates out were equal. But here we could say that at any time t, the volume is actually, that's in the tank. Remember, it's losing 1 gallon per minute. So it starts at 60, but then any minute it loses 1 gallon. So 60 minus 1t, or just 60 minus t. So therefore, the concentration out will be x over 60 minus t. Okay, so that sets up the givens, our equation again. dx dt is r sub I c sub I minus r sub O c sub O. So dx dt is r sub I is 2, c sub I is 1. Those are always going to be constants. Minus r sub O is 3 times c sub O, and c sub O is the x over 60 minus t. Okay, so I'll write that as follows. I'll say dx dt is 2 minus 3 over 60 minus t times x. Okay, because again, remember, the standard form we're shooting for is dx dt plus p of t x equals q of t for the first order linear. And so we'll move the x term to the left to obtain that form. So dx dt plus 3 over 60 minus t x equals 2. And now we need the integrating factor. So rho, again this is rho of t if you like, it's going to be e to the integral of p of t with respect to t. Okay, so that'll be e to the integral of the 3 over 60 minus t with respect to t. So if you want, you could factor out the 3. So e to the 3 integral 1 over 60 minus t with respect to t. But then integrating that, we get the natural log, but we have to modify it by a negative. Because if we take u to be the denominator, the du is minus dt, so we'd modify by the negative, so we'd get e to the negative 3 natural log of that denominator. And so then, taking the negative 3 to be the power, we have e to the natural log of 60 minus t to the negative 3rd. So therefore, rho of t is 60 minus t to the negative 3rd. So then we multiply. by the integrating factor. So we get 60 minus t as a quantity to the negative third times dx dt plus 60 minus t to the negative third times 3 over 60 minus t times x equaling 2 times the quantity 60 minus t to the negative third. So then let's simplify that a little bit. 60 minus t to the negative third dx dt plus, this would be 3 times 60 minus t to the negative fourth, because this is really the first power in the denominator, so subtracting exponents, if you want to think of it that way. Minus 3 minus 1 is minus 4, and that equals the right hand side. So now the left hand side is the derivative of the product of the integrating factor 60 minus t as a quantity to negative 3 times x, and that's going to be equal to the right hand side. Okay, now we're going to integrate both sides, so I'm just going to throw the integration symbol in front of each side and the differential dt to the left. Okay, or to the right, that is. On the left, the integral of the derivative of something is just the something, so we get 60 minus t to the negative 3 times x equals, okay, when we integrate this, we have to use a u substitution. U is going to be 60 minus t, du is minus dt, so minus du is dt, and then we'd have 2 times the integral, minus 2 times the integral of u to the negative 3 with respect to u, and that would give us minus 2 times u to the power of 1 greater is negative 2 divided by negative 2, and so we get u to the negative 2, or just simply 60 minus t to the negative 2 plus our constant. Okay, so that's the integration of the right hand side. So a lot of times, as we've mentioned before, you know, if you're doing a detailed solution such as this, some of the basic integrations you want to take off to the side or do on scrap paper. Okay, now we need to solve for x, so we're going to divide everything by the 60 minus t to the negative 3. So I'm showing it explicitly. And now we have x is, okay, this gives us 60 minus t to the first. Subtracting exponents, minus 2 minus a minus 3 would be plus 1. And then plus, let's express this as c, and we'll bring that negative exponent up to the numerator. 60 minus t is a quantity cubed. Alright, so now the initial conditions will give us the constant c at t equaling 0, the amount x was 0, so then we'd have 0 equals, this would give us 60 plus c times 60 cubed. So then c is negative 60 over 60 cubed. So C is negative 1 over 3600. So then we get that x of t, and then the function of t at any time is equal to, I'm going to write it 60 minus t. I won't include the plus or the 1 exponent, but then minus 1 over 3600 times the 60 minus t quantity cubed. Okay, so that's actually just part A. I didn't label these, but if you go to the top, you can label this as part A if you want. And part B, it says, what's the maximum amount of salt at any time? Well, if you remember from Calculus 1, max and mins, because x is the amount of salt, if we want the maximum salt, maximums and minimums are found by setting the first derivative to 0. So therefore dx dt we're going to set to 0. We'll give the max or the min. So dx dt is just the derivative. So this is x prime of t. And so that's going to be the derivative of 60 minus t is just minus 1. Here we need the general power rule. Swing down the 3 times 1 over 3600. And we get 1 over 1200 times the quantity 60 minus t, power 1 less 2. Then don't forget the derivative of what's inside, and the derivative of negative t is negative 1, so that makes this positive. So then the maximum occurs when negative 1, when this quantity is 0, basically. Alright, now we need to solve that. So first bring over the 1, multiply by 1200, get 60 minus t as a quantity squared equals 1200. Take the square root of both sides. 60 minus t equals plus or minus square root of 1200. And that would mean that, let me come over here, that would mean that t is equal to 60, let me say minus plus the square root of 1200. Because what I did there in a clever way is I brought the t to the right and then brought this to the left. So instead of plus minus, I changed it to minus plus. But then the time has to be less than 1 hour because the tank runs out in an hour. So it can't be the first. It has to be less than 60. So it can't be the plus because you'd have 60 plus something. So then our answer must be that t is equal to 60 minus the square root of 1200, which gives us 25.36 minutes. Okay, so then the amount is x of 25.36. So plugging in 25.36 into x, that's, what's that, cubed, right? Alright, so then you're going to get 23.09. And that would be pounds. So, okay, so that's it for that example. Probably would never ask you about a maximum, just finding the function and maybe a time, but that's how we would do that one. Alright, so that's the end of 1.5.